You know that feeling when you're pushing your phone really hard, maybe playing a game, and it starts to get warm in your hand? Well, that warmth is the result of a constant, invisible battle happening inside, a battle against heat. And in this explainer, we are pulling back the curtain on the secret weapon engineers use to win that fight. It's a surprisingly simple trick, really, that turns a super complex physics problem into something you probably remember from high school. Let's dive in. Okay, so here's our game plan. We'll start by talking about why heat is such a huge deal for all our electronics. Then, we'll get into the basic physics of how heat actually moves around. After that, we'll reveal the really clever analogy that makes solving this whole thing possible. We'll see how to apply it, and then we'll run the numbers and find out if our imaginary device is going to make it. So, first things first, let's really understand the problem. You see, every single electronic component, no matter how small, generates heat. It's just waste energy. And as our gadgets get smaller and faster and just way more powerful, getting rid of that heat turns into this giant, critical puzzle for engineers to solve. I mean, just think about it. We are cramming more and more power into these tiny, tiny spaces. This creates these incredibly intense hotspots. And if you can't pull that heat away fast enough, the device is going to slow down, or worse, it could literally cook itself from the inside out. So getting rid of heat isn't just some small detail. A lot of the time, it's the single biggest thing holding back performance. And hey, don't just take my word for it. This quote from an MIT professor really nails it. He's basically saying that how good your gadget is directly tied to how good you are at cooling it. It's that simple. Better cooling means better, faster technology, period. So to actually solve this problem, you first have to understand it, right? So let's jump into some of the fundamental physics and look at how heat actually gets from point A to point B. Turns out there are really only three ways heat moves around. First, you've got conduction. That's heat moving through a solid thing, like the handle of a hot pan. Then there's convection. That's when heat gets carried away by a moving fluid, like the air from a fan that cools your computer. And last, there's radiation, which is heat traveling as invisible light, kind of like the warmth you feel from the sun on your face. Now, here's what's really useful for engineers. At the temperatures we're talking about inside our phones and laptops, radiation is actually a pretty tiny piece of the puzzle. So they can simplify the whole problem by just focusing on conduction and convection. Those are the two heavy hitters, the main ways heat is going to escape your devices. And that brings us to the real heart of this explainer. This is the elegant aha moment that makes this whole complicated problem manageable. This is the engineer's secret weapon. You see, trying to solve all the complex physics equations for heat transfer, well, it can be a nightmare. It's really, really hard. But what if you didn't have to? What if you could just translate the entire problem into a language that every single engineer already speaks fluently? A basic electrical circuit. And this right here, this is the magic trick. You can map the entire thermal system directly onto an electrical one. The difference in temperature, which is what makes heat move, that's your voltage. The flow of the heat itself, that's your current. And how much a material fights against that heat flow? Well, that's just good old electrical resistance. With this one simple analogy, a crazy hard thermal problem suddenly becomes as simple as Ohm's law, V equals I times R. Let's break that down real quick. So just like voltage provides the push to get electrons moving through a wire, a difference in temperature is what pushes heat to move. A really big temperature difference is like a high voltage. It makes a whole lot of heat want to get moving. Okay, next up is heat flow, which we measure in watts. This is just how much heat energy is moving from one place to another every second. In our little model, this is exactly the same as electrical current. It's just the flow part of our circuit. And finally, we have thermal resistance. This is a big one. Some materials, like copper, let heat zip right through. They have a really low thermal resistance. Other things, like plastic or just air, are great at blocking heat. They have a high thermal resistance. And that's exactly, and I mean exactly, like an electrical resistor that opposes the flow of current. Okay, so we've got our analogy down. Let's see how it works in the real world. We're going to trace the actual physical path that heat has to take to escape from a computer chip, and we'll build our circuit as we go. So the journey begins at the junction. That's the super hot spot deep inside the silicon chip where the heat is actually created. From there, it has to travel through the chip's little plastic or ceramic package, which is called the case. Then it has to get into the metal heatsink, and finally, it has to make the leap from the heatsink into the ambient air around everything. Every one of those steps is a hurdle. And now, here is the really cool part. Every single step in that physical journey, from the junction to the case, from the case to the heatsink, from the heatsink to the air, each one can be modeled as a simple resistor in a series. The whole complicated path just turns into a straight line of resistors. Now, of course, in the real world, you've also got stuff in between those parts. You've got thermal grease, that gooey stuff, or special pads. They're super important for making sure heat transfers well, but they're not perfect. They have their own resistance to heat flow. So guess what? We just add another little resistor to our circuit model. Easy. All right, we've built our model. It's time for the payoff. Let's plug in some actual numbers from a components datasheet and calculate the final temperature. We're going to find out if our design is any good. First, we need to know how much heat we're dealing with. This is our current. So let's say our component is spitting out 10 watts of power. That's the amount of heat that's going to be flowing through our entire thermal circuit. Next, what's our starting point? This is kind of like our ground voltage. We'll say the air around the device, the ambient temperature, is 40 degrees Celsius. It's a pretty warm room. And finally, the resistance. After we look up all the values in the datasheet and add up all the individual thermal resistances for every step of the journey, the junction, the case, the grease, the heatsink, we get a grand total of 7.8 degrees Celsius per watt. And it all comes down to this one simple equation. The final temperature deep inside that chip, the junction temperature, is just going to be the starting temperature of the room plus the total temperature rise. And we calculate that rise with our thermal Ohm's law. The heat flow, Q, times the total thermal resistance, R theta. Okay, let's plug it all in. We've got 40 degrees to start with, plus our 10 watts of heat, multiplied by our total resistance of 7.8. We run the calculation and we get 118 degrees Celsius. That is how hot the core of our chip is going to get under these conditions. So, here's the million-dollar question. Is 118 degrees too hot? Is it going to survive? We grab the components data sheet, and it tells us the absolute maximum safe temperature is 150 degrees Celsius. Our calculated temperature? 118. We're well under the limit. Success! The design works and our component is safe. So we've just seen how this incredibly powerful yet simple analogy helps engineers keep one single tiny component from melting. But it kind of leaves us with a much bigger question, doesn't it? How do you scale this thinking up? How do engineers apply these exact same principles not just to one chip, but to the thousands and thousands of servers that power the internet, to cool an entire data center?